So let's see.
We usually, shouldn't we be writing our password down somewhere?
First stop.
Middle southern latitudes, the part of Mars where we find these active slope features, and we're zooming in on the Newton Basin crater here. What you can see are lots of gullies. The active features that we've recently discovered are on the slopes that are facing mostly to the north, to the equator. What we see are much smaller scale features than gullies. You can see an area of bedrock, a steep cliff here, and it's from that bedrock that these dark features flow out. Given the latitude and the slope aspect, in particular the temperatures, it suggests that there is a volatile involved here, and the appropriate volatile for this temperature is water. Probably salty water, because sometimes these are active when it's a little bit below the freezing point of pure water. Salt lowers the melting point. And water on Mars should be salty. We know there's lots of salts on Mars. This is potentially actual water in a liquid state flowing on Mars today, not millions of years ago. And in late spring and into the summer is when these features form and fade. By late summer, early fall, they'll be completely gone, and we'll see just a normal looking slope throughout the winter. Every place where we have multiple years, these features recur. They're not exactly the same. They may be more or less active one year than another, but they keep coming back.
Okay, so we've seen the kind of animation of these features here, and as the narrator mentioned,
But they keep coming back. Recur, they're not exactly the same. They may be more or less active one year than another, but they keep coming back.
Okay, there's one other volatile which wasn't mentioned there that also exists under these conditions. And I'll give you a hint. This is the Newton crater. Anybody know what it might be? Very simple. Big juice. Big juice could naturally occur in the Newton crater, and that's just throwing it out as a possibility. About the same consistency of water, but actually we don't really think that that's the case. But anyway, but as the narrator emphasized, this is the first evidence that we have for flowing liquid water actually on Mars to this day. So of course we would like to explore that kind of an area, but it's challenging, as you can see, because of the slope and everything. But the presence of actual liquid water means that there is still the possibility of life even on Mars currently. Okay, so moving on to finish talking about possibility of life on Mars, we have these Martian meteorites, which we discover on Earth, in the south polar regions of Earth. And we actually know that they're from Mars because of atmospheric evidence that we see. They're sort of potato-sized meteorites, much smaller than this, or they're small. And inside them we see a variety of different things that are interesting. We see things that look almost like fossilized microbes, but we also see the evidence for some sorts of organic types of compounds. All right, so how do we know they're from Mars? Well, gases trapped in bubbles in the rock have a composition that's identical to the samples obtained by Viking in 1976. So when Viking landed there, it stuck out a little probe and it measured the atmospheric composition and radioed that back, and that's how we found out that there was 95% carbon dioxide and all these other trace gases. But when we drill into some of the trapped air bubbles in these meteorites, which have gone through space for hundreds of thousands of years, you actually can still get a little sample of Martian air. I think they're going to they're probably going to market a line of Martian air pressures, where you get this great little bubble and breathe a little bit of Martian air. But that's how we actually know that they're from Mars, little areas that actually have trapped material. And what we measure is a distribution of gases that just exactly mirrors what we measured on Mars in 1976, 96% carbon dioxide and the appropriate level of trace elements. So there's no real doubt that this certain class of meteorites that we find at the South Pole on Earth actually are from Mars. Now, I don't mean to say that all the meteorites that you find on Earth are from Mars. It's not true. It's just a tiny little set. It's really pretty difficult to get a meteorite from Mars to the Earth, because what happens was Mars was hit by a huge asteroid, and Martian material was flung into space, and it went every which way in space, but some tiny fraction of it, just by chance, ended up on orbits that intersected Earth, and would have re-entered the Earth's atmosphere and landed all over the world, but they're easier to collect at the South Pole because you can just see them flying around the surface there. All right, so to go further with this, we actually measure polycyclic aromatic hydrocarbons, which are associated with decay microbes on Earth, and we also see things that look kind of like little microbes out of microbe conventions there. About heading into the microbial mosh pit. I'm sorry, weird. I'm heading over that way right now. All right, so the idea is that we could have had microscopic life on Earth at some point. That's the re-entry of a Martian meteorite right there. So the scenario is that we had microscopic life on Mars when there actually was liquid water and thick atmosphere prevalent. At that time, a large asteroid impact would have flung a lot of this material into space, and then, actually my time estimate was off. I said about 100,000 years. We're really talking around 15 million years. And then a tiny number of those things landed in Antarctica around 13,000 years ago. And then what happened was they went through a glacial process. Glacial flows of ice at the South Pole tend to accumulate stuff in a certain region of the South Polar area. And if you go there, you tend to see a sort of a rock collection. But it's not just a collection of any old rocks. It's almost always meteorites, because there's no naturally occurring rocks in the ice anyway. So the stuff that collects in this area is always meteoritic in composition, and you can go out there with a snowmobile and actually pick the stuff up. All right, so to go through the list of issues here, we do think that it's true that this class of meteorites really are from Mars because of the composition of the trapped gases being an exact match for what was measured on Viking. Now that's not really debated anymore. I think most scientists agree about that. There were early on questions about whether the meteorites could have been contaminated by Earth. After all, they moved through Earth's atmosphere. Earth's covered with organic material. But we think that the polycyclic aromatic hydrocarbons we're seeing in the meteorites are actually of non-terrestrial origin, because the concentration is greater as you go towards the center of the rock. Now you would think if it was earthly contamination, it would be, of course, stronger around the edges. There's a possibility that chemically, things like polycyclic aromatic hydrocarbons actually could be produced in space by exposure to cosmic rays. So one could look at that possible process and say, oh, they're not really, it's not fossil material, it's just some weird exotic chemistry that happens in space. But we basically don't see this exact composition in other meteorites, so it seems to be an exclusive class. The fossils are pretty small, a bit smaller than earthly fossils of bacteria. We don't really understand that too well. But the bottom fell out for this interpretation. Now you got to remember, we're following the scientific method here. This is only around 10 years ago or so. It's pretty recent. So all of this positive evidence turned out to be outweighed by very clear negative argument that gets made. Based on rock samples brought back by the Apollo astronauts in the 1960s and 1970s. I mean, who would have thought that you'd go to a museum of Apollo rock samples and be able to pull out something that actually answers the question from really current science? Well, what they did was they actually just cut open some of those meteorites, not meteorites, but rocks that were brought back from the moon by the Apollo astronauts, and they just found similar kinds of structures inside those rocks. Now, the moon never was a site for life. We're virtually 100% certain about that. So if you see little fossily-looking things in the moon rocks that look like the ones that were in the Martian meteorites, you pretty much have to discount that as evidence for life on Mars, because otherwise it would imply life on the moon, and we're pretty sure that that never possibly happened. So even though the meteorites are from Mars, we don't think that they actually represent fossilized evidence for life on Mars in the past. You still have the possibility of the methane gas. As I mentioned, that's kind of dissipated. The methane gas argument is kind of dissipated along with the methane gas. So that's kind of still under investigation right now. There are other intriguing areas that we can look at, like for example, Saturn's largest moon, Titan, actually has a thick atmosphere of its own, which might actually be thick enough to support the presence of liquids on the surface of Titan. So that's another area that would be interesting to look at for life. Okay, so Mars has 2 moons. They're pretty small. They're probably captured asteroids because they're just about the size of sort of mid-sized asteroids. One oddity about one of them, Phobos, is that it's so close to Mars that its orbital speed is actually faster than Mars' spin. So Phobos rises in the west and sets in the east. It actually turns out to be an unstable orbital configuration, so Phobos might even eventually crash into the piece of Mars itself. This Phobos, sometimes called the giant olive, the Mento area right there. And Phobos itself actually has little boulders and mini craters on it. And this is Deimos, a little bit of a smoother character. So again, these actually look like asteroids. We think they are captured asteroids. Okay, so that moves us on to Jupiter, which I'm going to have to try to get to a fair amount of, because that was actually the main topic today, and somehow we're actually kind of a whole lecture kind of schedule, so I don't understand. But there we have Jupiter. This is actually a regular color photo of Jupiter. So this is something you might actually see through well, I'm not sure any earthly telescope would actually show you this much detail, but this is actually a satellite-based photo. But we see the well-known great red spot, atmospheric bands. We're looking at an object here that's completely unlike any of the terrestrial planets. So now, even though Mars was kind of intermediate with that low density, nonetheless, Jupiter is completely different from any of the terrestrial planets. We're looking at a body that has no solid surface in there at all. It's not like this is the atmosphere and there's a body under it that's about as big as what I'm indicating. It's basically a gaseous planet pretty much all the way in. And deep inside there is a rocky core that's about the size of the Earth. So it's sort of like the Earth with a humongous, thick atmosphere over it. I like to show this table again just to indicate where we're going in the solar system. It's kind of our solar system GPS. So what we see is moving out to Jupiter's distance from the sun, we're now over 3 times farther, just in one jump, we're 3 times farther away from the sun than we were in the case of Mars. So remember that Mars is getting pretty cold, right? So Jupiter is going to be a lot colder. We're 3 times farther away from the sun. And that drop in temperature is going to have a lot to do with the new composition and structure we're seeing for the first time in the outer solar system. And you can see if you look at the density column on the far right, as we move from the terrestrials to through Mars here, we start to see a little bit of a drop in density because Mars doesn't have a lot of heavy material like iron. And I mentioned that this is sort of differentiation in the solar system itself, where the dense material tends to stay close to the sun. Well, you can see that effect continue when we get to Jupiter, because Jupiter's density is only a little over 1 gram per cubic centimeter. 1 gram per cubic centimeter is the density of liquid water. So what we're seeing here is a planet that's really got a completely different structure and composition from any of the terrestrials, and continues this ongoing theme of less dense material as we move away from the sun. This idea of the differentiation of the solar system itself.